Now that we have looked at how we can use quantifiers to formalize propositions on the square of opposition, and we've developed our basic types, we're in a much better position to formalize categorical propositions and other more complex propositions. So to get a little practice at that, let's look at the propositions from lab exercise 4.1.1. Now you'll remember that these are all categorical propositions, and in that context we formalize them using the tools of categorical logic. What we're going to do this time is see how we can formalize these same propositions only using the tools that we've developed with quantifiers. So let's start with number one. Lassie is not a Cocker Spaniel. So obviously in Lassie is not a Cocker Spaniel, we have, let's define the function c of x as blank is a Cocker Spaniel. Okay? Okay. Now we also have the individual L. We're going to use a lowercase letter to represent Lassie. And so to formalize Lassie is not a Cocker Spaniel, we're going to use C of L, and we're going to negate that. So it's not the case that Lassie is a Cocker Spaniel is a pretty fair representation of the meaning of Lassie is not a Cocker Spaniel. Okay, so now let's look at number two. That was number one. Number two. Number two is most CDs cost more than $10. So now, a little reflection. We don't have a most quantifier. We have either all, the universal quantifier, or some, the existential quantifier. So, since most is not the same thing as all, the closest we can get to it is to use an existential quantifier, or in categorical logic, a particular. So in categorical logic, we would formalize this some CDs are, and then we have things that cost more than $10. All right. So what we have here is then, this is more or less what we would do with this from a categorical logic perspective, but what we have here is a proposition that is an I. It's in the I form, and as you recall from our discussion of quantification theory, the I form is going to use an existential quantifier, and we're going to have the subject term and the predicate term. So this is the logical form. So now we just need to figure out what the specific functions and arguments are. So let's use C, in this case, to stand for blank is a CD, and let's use T to stand for blank costs more than $10. Okay, just like that, okay? Now, what we're saying in the original sentence, or at least in the categorical form of the original sentence, shifting from most to some, is some CDs are things that cost more than $10. So what that means is that there's at least one thing such that that thing is a CD and that thing costs more than $10. So this formalizes the same basic meaning as the categorical proposition here, but using the form of an I that we developed when we were looking at using quantifiers to represent the propositions on the square of opposition. So here's our formalization. There's at least one x such that C of x and T of x. So a quick reminder here, the major operator inside the scope of the quantifier for i's and o's is and. The major operator for propositions that are universal is material implication. Okay, good. Let's move on to another one of these. How about number 3? If you wash my car, then I'll give you $20. Now, in exercise 411, the correct answer to that exercise was that this is not a categorical proposition. We now are in a better position to see that it's actually something we can capture pretty well with propositional logic. So if we use only propositional logic and let W stand for you wash my car and T for I'll give you $20, then the proposition can be formalized as W implies T. Now again, we're treating this W and T as propositions, not using quantifiers. In other words, we're not analyzing the interior of the proposition, but the thing is, we could. So if we define W of X as blank, wash or washes my car, and T of X equals I'll pay X $20. Notice the argument can go wherever it makes sense for it to go in the propositional function, in the function that we're representing here. So we're letting T of X stand for I'll pay X $20, right? So now we can formalize this with greater detail as W of Y. Let's let lowercase y stand for U. So W of Y actually formalizes you wash my car, implies that T of Y, I'm giving you $20, or I'll pay you $20. So this is a deeper analysis of the same thing that this captures. Here we're looking at only propositions and how they relate together. Here we're looking at propositions, but we have the ability using quantifiers to look inside the proposition, as it were, and discern the propositional function and also the argument. Another thing to notice about number 3 is, like number 1, no quantifier was needed because we're not talking about at least one thing or every member of a set. We're talking about a specific thing. In this case, the specific thing, the argument is you. So you being a specific thing doesn't require a quantifier because we're just talking about you or Lassie or Matthew or whatever, right? Okay, good. Now let's have a look at number 4. Some hives do not have bees. So in this case, it's pretty straightforward that this is a categorical proposition. What type is it? It's an O probably. So some some hives are not, and let's let B stand for things that have bees. Okay, so that gives us an important clue, well actually 2 clues about it, the way we're going to formalize this. So here's our basic structure from a categorical perspective, and if you think about what the form is for an O using quantifiers, what we have is for any X, S of X, and not P of X. So that's our basic form using a quantifier, or using quantifiers for the O-type proposition. So from this it emerges that if we let H stand for X is a hive and B stand for X has bees, then we'll be able to formalize this as there's at least one X such that X is H and not X is B. So what this means is there's at least one thing such that that thing is a hive, but does not have bees. And that is exactly what the original proposition is trying to say. Okay, let's do a couple more. So now, in number 5, we have either you have done your homework or you don't. Either you have your homework or you don't. So number 5. So again, from the perspective of categorical logic, that's not a categorical proposition. It's better captured as, let's let H stand for you have your homework, or it's not the case that H, you don't have your homework. So either you have your homework or not. So from a perspective of just propositions, that would be a pretty good formalization where H stands for you have your homework. But using quantifiers, we can look inside that proposition and we can define H of X as, as blank, or X has X's homework, right? We don't want to build your in there because then we might end up with someone else having your homework, so we don't want that, right? So we'll just have X being the argument here. So X has the homework that belongs to X, right? So now what's the argument here? In this case, again, it's U. So we're going to use a lowercase y to stand for U, and we'll be able to formalize the whole thing as H of Y, or it's not the case that H of Y. And what does this mean? It means either you have your homework or not. Okay, good. Let's have a look at 7. Number 7. I'm skipping number 6. Let's look at number 7. So in number 7 says Panama hats are made in Ecuador. So now the most plausible formalization of that from the perspective of categorical logic is all Panama hats are things made in Ecuador, right? So this is our clue, and the other cue that we're going to pick up is that an A proposition is best formalized with this form. For any X, S of X implies P of X. Notice a couple of things. We're using the upside down A as a universal quantifier, and then here we have the domain maker, basically, is X is S, implies that X is P. Another way to think about this is that for any X, if X is an S, then X is a P. And that's what we want here, right? So for any X, if X is a Panama hat, then X is made in Ecuador. And there's our formalization. So notice it parallels this pretty well using the form that we have derived for the universal affirmative on the square of opposition. Okay, let's do maybe one more example of a universal. So looking down this list, let's do number 8. That's an interesting one. The Python is a Boyd. So Boyd, boidae, Boyd, that's the family that Pythons belong to. So what the speaker is actually saying is that if anything is a Python, then it is a member of this family. So that's essentially all Pythons are Boyds. And so here again, drawing on the form, we'll say for any X, if X is a Python, then X is a Boyd. And that, once again, that draws on that general form of the universal affirmative, and then, of course, filling in the terms. The X is a Python, X is a Boyd. Let's do, just for fun, let's do 14. So number 14 says only logic students are worthy of admiration. So what does that actually mean? Well, remember, our way of formalizing sentences that start with only is to try to clarify which set contains every member of the other set. So is it the case that every member of logic students contain the set of people who are worthy of admiration, or is it the other way around? So what happens is because only sort of reverses that, it's the other way around. So what we would formalize is all W, all those worthy of admiration, are L's, the logic students, right? And so here again, it's a universal affirmative. So we've got, for any X, if X is a W, then X is a logic student. So what does that say? That it says basically only logic students are worthy of admiration.